Hello everyone, I am Rongzheng and this is Yumeng. We come from Shandong University. Our talk is titled Implicit Multidimensional Projection of Local Subspace. Here is our outline. Multidimensional data is everywhere. We usually reduce their dimension and then visualize them with secant plots. Some dimension reduction techniques aim to preserve global structures, while others preserve local structures. However, the traditional secant plot misses orientation information from the linear structures. For example, this is a dimension reduction result of a phase image dset with MDS. There are two trains crossing at the center, but it couldn't be noticed from the left secant plot. To solve this problem, we propose a visualization method to understand the effect of multidimensional projection on local subspace. Now, these manifold structures can be seen, and some interesting local patterns can be focused. Now, I will introduce related work. Some work visualize the quality information in the secant plot. For example, check ways visualize distortions with a 2D color map applied to Voronoi cell partitions. And probing projections visualize the local stress matrix of MDS. Relating results with original data dimensions is another way to interpret them. For example, dim reader represents the original dimensions by isolance, and Cavallo proposed an interactive framework allowing the user to visually explore forward and backward projections. Flow-based and generalized sensitivity secant plot encode local trends as glyphs, and one glyph encodes cluster information as arcs. However, their local patterns are not defined by the whole original data dimensions. Here comes our method. This is our pipeline. Our method extends traditional secant plot in three ways. First, we extract the local linear subspace in the original space and perform PCA on k nearest neighbors of each point. Second, we transform the eigenvectors using implicit differentiation. Third, we visualize data with local subspace information using 2D ellipse-like glyph. We identify the local linear structure around a data point using k nearest neighbors method. Then we perform PCA of the neighborhood and obtain its eigenvectors and the corresponding eigenvalues. So, the local neighborhood can be fitted by a multidimensional ellipsoid. Then, we transform these vectors into 2D space. And the most important thing is to get this Jacobian matrix. For linear dimension reduction method, the Jacobian matrix is identical to the matrix from the linear map. So we can easily get the vector transformation according to this projection matrix. However, most of the nonlinear methods are more complex. We can't get an analytic derivation of Jacobian matrix. The standard approach is to employ finite differences. In this way, we need to perturb the original data and do dimension reduction again. But there are two shortcomings. The first one is high computational cost. We have to compute many times of dimension reduction. Second, it needs to modify the original data. As we know, dimension reduction techniques are dependent and often works only on the given input data. The additional points may modify the projection itself. So we propose the implicit vector transformation method. As we know, nonlinear projection usually has a relationship between the original data P and the projected point πP by optimizing an objective function. As a result, point πP lies in a local minimum. In other words, the partial derivative is zero. We can find that this is an equation of P and πP. So we can regard the relationship between P and πP as an implicit function. Take the partial derivative with respect to P on both sides of this equation and apply the chain rule. And this is the Jacobian matrix. Now what we need is to compute these two matrices. And then we can compute the vector transformation with our implicit differentiation.
After vector transformation, the next step is glyph generation. If we directly visualize our vectors as lines, it might cause visual clutter that impairs perception. We noticed that only the long vectors are important, so we generate a convex hull. To let it smoothing, we use the convex hull's vertices as control points and design a closed B-spline curve. As you can see, it not only can represent the major transformed basis vectors, but also is smooth and easy to distinguish. As we know, the quality of the dimension reduction method for data points is very important for visual analytics. Here, we introduce three metrics to describe the projection quality, including projection error, neighborhood preservation, and linearity. And we can color map the glyphs with these metrics. Now, let's go to numerical evaluation part. This is synthetic planar data sampled on 3D record grid. We projected it to 2D with MDS and compare our implicit vector transformation method to the approximated random approach using finite differences. As you can see, our results are more like a normal circle. Here you can see the histograms of angles between two transformed vectors of non-border data points. As you can see, our angles are closer to 90 degrees. And this table shows other statistics. We can see that our method has a small difference of mean lengths of two vectors and has a lower standard deviation of angles than the random method. Furthermore, we conducted some studies to demonstrate how our method can be applied to real-world datasets and help people to perceive hidden data patterns. Here is a dataset of 3 object images. We reduced its dimension with PCA. We can see that the transition of orientations of glyphs matches that of the dark images. And 5 large glyphs are associated with backwards facing cars. And in MDS result, there are also crossings associated to the change of darks and blocks. This data contains face images of different camera positions and lighting conditions. This is PCA projection colorized by trustworthiness. In the left rooming, there are three distinct types of glyphs corresponding to the face images with three distinct orientations. And there are two types of images in the right rooming. And these are results of seed data. The glyphs form a twisting structure crossing. In conclusion, we proposed a model to visualize local subspace for multidimensional projections, and an analytical vector transformation method based on implicit function differentiation. Finally, we design a glyph representation that shows the geometry of transformed basis vectors of local structures. Thank you for your attention. More details can be found in our website, and the code can be downloaded from the GitHub.